Okay, modeling logarithmic functions. So this tutorial will just take you through log functions, kind of walk you through the process, all that fun stuff to go along with it. It'll just give you a better understanding of things, definitions, all that fun stuff. As usual with the tutorials, I typically will not answer the questions unless I feel like it's important for your understanding or lesson. And I'll let you watch the videos on your own. Most of the time, I'll let you do the questions on your own as well. So let's get into it. And we'll just go over logarithmic functions. And I have a couple other like little mini lessons on my YouTube that show some logarithmic functions and that gives you a better like breakdown and understanding of everything. But first, we have exponential function. Now, take a look at the exponential graph we have here. And as you can see, exponential function, it increases dramatically. So exponential function, a function that includes the independent variable as part of the power in the exponential expression. See how it's increasing dramatically as time goes on? Hours 1, 2, 3, 4, and then it goes from 1, 2, 4, 8, 6. So it's, or 16. It's getting increasing. Inverse function. Well, a function that reverses or undoes the action of another function. In an inverse function, the x and y coordinates are all solutions. All the solutions are reversed. Pretty interesting, actually. And this shows that just graphing a logarithmic function, a function that includes the independent variable inside a logarithmic expression. Okay. Now let's go on to logarithmic functions again. And this shows you the reverse. Like I said, if you look at my YouTube channel, I have a brief, small mini lesson that talks about log functions and just basically the properties of logarithm, because there's several different rules and properties that go along with it. It does get a little bit confusing. So this just shows you how it's reversed when you have log of bm equals x, and then you go b to the x power equals m. And same thing like this, log of 2y equals x, 2 to the x equals y. Shows how it reverses each other. Okay, and then click on the spot on the graph. So we'll click on each spot on the graph, okay? So this first part is the range. The range is a set of all y values that are an output of the function. So the range of f of x equals log 2x equals negative infinity to positive infinity. Okay, let's go to the next part on here. Aha, the x-intercept. That means it is touching on the x-axis. So the point at which the graph crosses the x-axis or touches the x-axis. So think of it as the line or the point is going through the x-axis, it's touching it, crossing through, something along those lines. All right, let's click this part. Vertical asymptote is as x approaches 0, the value of f of x decreases to the negative infinity. This behavior occurs because we can't take the logarithm of 0. So that's why it would be, it decreases to the negative infinity. Now let's go to this line here. This is the domain of our graph now, okay? So think of this part as our domain. And the domain is the set of all x values for which the function exists. Shape of the graph. So graphs can look all kinds of different shapes, like typically curved lines, something like that. So for the small values of x, the graph grows rapidly as the value of x increases. However, the value growth, so the rate of growth slows for increasingly larger values of x. So the value and the growth are similar here. We got a lot going on here. And the end behavior of the graph. So end behavior describes what the graph does as x increases to positive infinity, decreases to negative infinity. It just tells us what's happening in our graph, okay? Here's our lovely little chart that shows each function we have going on here. Okay. This just is comparing 3 different functions together and what they would look like graphed out, and the range of each function is negative infinity to positive infinity, or all real numbers. So it'll always be like that for those types of graphs, negative infinity, positive infinity for the range. Remember that. Okay. Features of f only, so I'll go over this real quick. Features of f only would be negative over the interval 0, 1 increases as x increases. The features of both f and g, domain of 0, infinity, the x-intercept is 1, 0. Then the range is a negative infinity to positive infinity. Okay, asymptote is x equals 0. Now, positive interval, and this is for g only, features of g only. Okay, now we have positive over the interval 0, 1, it decreases as x increases. Okay, so now we have transformations. Shows how the graph is moving about, translating, it's going to be curving. So if you're familiar with it, geometry, when a shape is transforming, moving about the x and y axis, this is kind of the same process with our graphs, okay? So a manipulation of an object or a curve by sliding, stretching, and compressing. So we're moving the line, we're sliding it over, we're making it bigger, smaller, something along those lines, okay? Question, I'll let you do this question on your own. This just shows a better example of transformations. It's giving you an idea, tells you vertical dilation, what happens when it's a vertical dilation, and how it is stretched. This is what happens when it is a reflection. So a reflection, it's kind of flipping over on the opposite side. Horizontal shift, it's moving horizontally, so it's moving like kind of in a line. Think of like the sunrise or sunset is on the horizon, kind of like that straight line, kind of moving that way. Vertical would mean up and down. So vertical shift, up and down. Questions, we'll let you do this on your own as well. Let's go over the definitions real quick. Domain of this function, we have this. It gives you the domain, what's going on with our function. Range for this function. Now, range is usually negative infinity to positive infinity. That's very typical with the range. And behavior is just showing what happens as it's reaching both negative infinity to the positive infinity. Intercepts would be where it's intersecting on the x-axis and the y-axis and what's going on with that. The vertical asymptote function, it has a vertical asymptote of x equals 0 because the horizontal shift in the vertical asymptote function is 4 units to the left, x equals -4. So that just talks about that. All right, let's go to our graph again. Just gives us an idea, domain and range, and it tells us more about these graphs. Okay. Then we have, let's see, we have another graph, we have another example. Video, I'll let you do the video on your own, and these questions too. So logarithmic models, and now we have, whoops, let's go here. Exponential models, let's talk about this real quick. Recall the general form of the exponential model. So a lot of other tutorials and mini lessons I have, if you go back on my YouTube channel, I have several lessons on exponents, solving for exponents, graphing them, all of that stuff. Definitely go back if this is confusing. So we have f of x equals ab to the x power. In this form, a represents the initial value and b represents the factor by which f of x changes for every 1 unit increase in x. Think about that. Exponential, so it's increasing exponentially. The number keeps getting bigger, 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 just like that. Kind of goes up like almost a straight line-ish. Okay. Now it just gives us another example. Okay, this is just going to give us a couple other examples of equations. logarithmic models, all that fun stuff. Let's go to the next part, question. Like I said, I'll have you do these questions on your own. Yeah, we'll skip that one too. Logarithmic scales. So a logarithmic scale, just real quick, is a nonlinear scale that quantifies a larger range of values in the logarithmic scale. Each interval, it changes by a factor equal to the base of the logarithmic used in the scale. Okay, so what that means, it's a larger range of values. So it starts off like there's a smaller number, there's a bigger number. So you have like a whole wide range of values in it, from super small to super large. Think like how they have the example earthquake intensity. Okay. We can learn more about that later. So let's skip this question. The Richter scale to measure earthquakes is a good example of logarithmic functions and models. And this just clears up. I'll show the definitions once more. And hopefully this clears up modeling logarithmic functions a little bit better, and hopefully gives you a little bit better of an understanding of exactly what is going on during a logarithmic function and or model. If it is still confusing, I definitely recommend you taking a look at some of the other mini lessons I've done with log and exponents, because it'll break it down just a little bit more for you and hopefully make it even less confusing. And I think that is about all for now on this tutorial. And hopefully, like I said, hopefully that clears it up, and enjoy.